We are off to chapter 10 here, which should be the last exam, should be the last chapter that will be on our upcoming exam, which should be in a couple of weeks, I think, from now, maybe is when it's happening. So in this chapter, obviously, we're going to talk about energy. We can talk about different types of energy. We're going to talk about specific heat and how to do some of those energies type calculations. So let us get started on it. So a lot of times in sort of chemistry and reactions, and really what energy sort of deals with is the idea of what is known in sort of as thermodynamics. And one part of sort of thermodynamics is the idea of energy, which obviously we will talk about in this chapter. If you continue to take chemistry, you'll talk about some other thermodynamic sort of properties like entropy and Gibbs free energy when you get into 1B. But ultimately, sort of the study of thermodynamics oftentimes revolves around the idea of whether or not a reaction, for example, is spontaneous. Will it occur under these conditions? That's sort of what you are looking at. One of the first laws of thermodynamics is actually the law of conservation of energy, which we'll talk about here. So energy does sort of fall under this sort of topic. When we are dealing with sort of reactions that take place and the idea of energy, there's always the idea of, most of the time we think of energy as sort of a perfect sort of flow of energy from sort of one place to the next. And the idea of that is we oftentimes have places which are referred to as the system. The system is pretty much anything in the universe that we're interested in. So again, if you're doing like a chemical reaction, like you might be doing later today in lab, the test tube would be your system. Obviously, everything outside of it would be the surrounding. And the surroundings is basically everything outside of your system. And a lot of times when we talk about energy and sort of think about energy, we're thinking about really the flow of energy from perhaps the system to the surroundings, or even from the surroundings to the system when we do it. One sort of principle of energy that we talk a lot about in chemistry is that idea that if there is somebody that loses a certain amount of energy, there will be something that will gain the exact same amount of energy. So we never lose energy or anything like that. It's just really transferred from one place to the next. When we talk about systems, there's a few different types of systems we sometimes deal with. One's an open system, like your test tube, for example. It could exchange mass and also energy with the surroundings. A closed system would be like put a stopper in your test tube. You no longer you get the mass that's inside out of it, but it can still exchange energy and stuff with the surroundings. An isolated system is one where pretty much nothing's being exchanged. It's pretty much isolated. The mass, the energy is not going to really go out. So once again, here in an open system like your test tube, you could take out the mass. You also can, if you're holding on to it, for example, you feel the heat maybe coming off the test tube, put a stopper on your flask there, not going to allow anything to escape. But, you know, it can still kind of heat up or cool down and exchange heat. And obviously in an isolated system, you really won't have that. Later today, if you do that part where you put the zinc in the test tube, don't hold on to it. Test tube gets hot. Yes. So let's talk a little bit about energy. Energy is the capacity to do some type of work. We use energy to do some type of work, really. There's different types of energy that we sometimes deal with. There's chemical energy, which are energy that's stored, you know, within the structural units of chemical substances. A lot of times in chemistry, we talk about what's sometimes referred to as bond energy. And there's a certain amount of energy required to either break bonds or make bonds. So for example, if we had some bonds we wanted to make, we have basically two sort of guys, if you will, separated from each other. They have a lot of energy. You need to actually remove the energy. So they kind of slow down and they're able to kind of come together and bond with each other. So a process where we kind of make bonds is what is referred to as releasing energy. And it's opposite if we are going to, for example, break a bond. If we have a bond there, everybody's bonded together. We actually just put energy in. And when we put energy in, everybody gains enough energy. They can kind of wiggle away from each other, and that bond is broken. So energy is absorbed. These sort of processes where energy is released is what is referred to a lot of times as a exothermic process. Processes where energy is absorbed are what are known as endothermic processes. So endothermic, heat and energy is absorbed. Exothermic, heat and energy is released. Other types of energy, like potential energy, for example, is the energy based on its position of an object. The classic example, right, is the giant boulder on top of like the hill there that's about ready to fall. It has a certain amount of potential energy. That potential energy, if it should happen to kind of roll over the top of the hill there and start to come down, can be converted into kinetic energy. And that is the energy based on motion. And then it obviously will hit the ground and transfer all that energy as well. And it come to rest at a different potential energy. So the law of conservation of energy basically says that energy can neither be created nor destroyed, but it can be transformed from one form to the next. It's really the first law of thermodynamics, is that law of conservation of energy. So if you take sort of that boulder example, where you got the big boulder on the hill, it has a potential energy, it starts to drop, it picks up some kinetic energy, hits the ground, and ends up with a final sort of potential energy once it hits the ground, also going to give off all that energy to the ground. Hopefully nobody's underneath the boulder at that point, or it would pick up the energy. But the total amount of energy, again, is really just, you can think of it as being transferred. So this goes back to the idea of what I was saying earlier, that we think about energy, again, in the very simple idea of if somebody gives it off, somebody's got to collect it. So the difference between sort of the giving off and collecting is, for one part, either the system or the surroundings, it's an exothermic process, while for the surroundings, it would be an endothermic process. So if the system gave off the energy to the surroundings, exothermic for the system, endothermic for the surroundings as it picks up all that energy, and sort of vice versa. If the surroundings gave off the energy, it would be exothermic for the surroundings, and the system then would pick up all that energy and it would be endothermic for it. The amount of energy, say you had 50 kilojoules of energy that's being transferred, is the same. It's just represented differently, as we'll talk about, by the sign. One represents, you have positive or negative sort of value for energy, represents either an ectothermic process or an endothermic process that's going on. Any questions on that there? So as I mentioned before, our thermodynamics, really the study of the interconversion of heat and energy, and sort of the application, we're going to talk about it. When we talk about something like energy, or even pressure or volume or temperature, as you can see there, these are what are referred to as state functions. And state functions are pretty much the simple idea of, it doesn't really matter how you get there. What's really important is really just two things. It's basically where you started and where you ended is really the two most important things about the process there. And we see that in terms of something like potential energy. If we look at our two hikers there on the mountain, our blue hiker took the more direct route to the top of the mountain. Our kind of red hiker there took the scenic route around the mountain. In terms of potential energy, they both have the same potential energy because they both started in the same location. They ended in the same location. Just took the other guy a few different ways to get there. And when we think about sort of beginning and ending, or initial state and final state, when we think about chemical reactions, when we have a chemical reaction, we basically have reactants that go to products. And the reactants are our starting material, and our products are really the stuff that is formed. So in terms of a chemical reaction, really our reactants are our initial conditions and our products are our final conditions, which is why when we calculate something like what we see here to the right, the change in energy, delta E is the change in energy, it's final minus initial. Change in pressure is final minus initial. Change in volume and change in temperature there, final minus initial. So again, your kind of final state minus your initial state, where you started, where you ended, really the difference between those two is really the most important. When we calculate something like energy, and a lot of times when we calculate something like delta H, which is the enthalpy of a reaction, which we'll talk about in this chapter as well a little bit. Delta H is of a reaction is oftentimes calculated by taking the delta H of the products minus the delta H of the reactants. And delta H is the enthalpy. The change in enthalpy is a fancy word for basically the heat of a reaction, how much energy is either given off or absorbed as the reaction takes place. But when we do something like this to calculate it, we take products minus reactants, which again is really our final state minus our initial state. The difference between those two is how we get there. Now, not all reactions, it's important to note as well, not all reactions take place in sort of a one-step motion. You know, a lot of times we think of a reaction like A plus B goes to E plus F, and we think of it as, okay, it just all sort of happens in one move. And a lot of reactions really don't sort of occur that way. A lot of reactions are sometimes multiple, what are sometimes referred to as elementary steps, individual sort of reactions that when you add them together, you get the overall reaction that occurs. So for example, this maybe happens as like A plus B makes C plus D, then maybe C plus D react to make E plus F. These are two separate reactions that if we add them together, we could cancel out whatever's on opposite sides of the arrow. So C's on the left, C's on the right, so they cancel. D's on the left, D's on the right, they cancel. That leaves me A plus B, which is on the left-hand side of the arrow, to E plus F. So this reaction, for example, could have occurred in multiple steps, and there might be energy associated with each of these steps along the way. There might be a certain amount of energy associated to do this step, another certain amount of energy to do the second step. So the overall energy that would be necessary to do the overall reaction there would be found by actually just adding both of the steps together. The energy that happens for each of those steps would give you the total process in terms of energy to get to the end. So a lot of what we look at obviously is energy here when we talk about thermodynamics and this aspect of it. And energy really is sort of additive. It's like how much energy it takes you to get all the way to wherever you're going from or trying to get to. Let's look at some important sort of units for energy. And by the way, none of these are negative. This is just all PowerPoint, so none of these are negative as well as we go through here. But really important units for energy that we use a lot are a couple of units of joules. Joules is one unit, and kilojoules are two very common units of energy that we do use a lot. The relationship between that is the same as our normal sort of 1 kilojoule is 1,000 joules. So that is a conversion that's used a lot, going from joules to kilojoules. A lot of times answers are given in kilojoules in terms of energy when it's all said and done. Sometimes you do want joules, but that conversion is used a lot. I will say a relationship that might be more important in 1A than in this class, but it's good to note, is this relationship that if you have a joule, it equals a kilogram meter squared second squared. Again, in our class here, we probably won't come across that too much, but in 1A, you will see it in several different formulas that you actually have to understand that relationship between energy. The Nm is a Newton meter, which we don't really use at all, pretty much in chemistry, most chemistry classes, but that's what the big N stands for there, a Newton meter. Other really common units of energy that we do come across in this class and other classes is actually a calorie, and that's a lowercase calorie. It's a lowercase c. A calorie is the amount of energy that's required to raise 1 gram of water by 1 degree Celsius. And we oftentimes will use little calories and kilocalories as very common units. And the relationship there is 1,000 little calories is 1 kilocalorie. So that obviously is the same sort of conversion as 1,000 joules is a kilojoule as well. A relationship between calories and joules, which is a really important number, is that one that we see there in the middle-ish. 1 calorie is equal to 4.184 joules. This is also what is known as sort of specific heat of water, which we will see later on in this chapter. So that relationship for sure you should know. The reason I do say that we are talking about here sort of lowercase calories in terms of lowercase c is another sort of unit that pops up occasionally when you talk about energy. Is a calorie really a nutritional calorie with a capital C? So a nutritional calorie is actually 1,000 of the little calories. Let's write it like that, which is the same as 1 kilocalorie. So kilocalories and nutritional calories, obviously used in like nutrition and exercise and that, but it does pop up occasionally. So there is a difference. If you do see a capital C calorie, it's actually 1,000 of the little guys, the little C's. So there's a difference in terms of value of those two things. Any questions on that there? Yeah. Yeah, so one kilocalorie would be basically that. Yeah, that'd be the same conversion. Yeah. Any questions? You sometimes see it like on treadmills and stuff, right? Where they said how many calories you burn. So sometimes, right, say how many kilocalories you burn. So it's really more of a nutritional unit that's used a lot. How they figure out, the calories on the back of the labels. We'll talk a little bit about it in this chapter, when they say your candy bars, this many calories and stuff like that. That's how we can finally figure it out. We'll also talk a little bit about that towards the end of this chapter. So let's talk a little bit about another type of energy, which is thermal energy. Thermal energy is the energy associated with the random motion of atoms and molecules. Thermal energy is really based on how much molecules and atoms you got there, and pretty much the more atoms and molecules that are present, the more thermal energy somebody will have, or something will have. Obviously, the opposite is true. Sometimes thermal energy is maybe a little confused with temperature. We do use temperature to help us understand energy changes, because typically if something gains energy, what happens to the temperature? It goes up, right? So if like you start heating a pot of water, right? You're adding energy, the temperature starts to raise and all that good stuff. And obviously if you sort of remove energy, like put stuff on ice, you would reflect that by seeing the temperature sort of decrease. So there is sort of a difference between thermal energy and actual temperature. So an example would be if we had a cup of coffee that's maybe 70 degrees Celsius, it has a higher temperature than, say, a bathtub that's 40 degrees Celsius. But the thermal energy in the bathtub is a lot more, because obviously a bathtub is a lot more volume of, say, water than the water that you would have in the coffee cup. And the reason it's not reflected in the temperature, or the temperature difference, is even though the bathtub has a lot more thermal energy, that means there's a lot more molecules in water, for example, that you need to heat. And it takes a lot more energy to raise the temperature of it. As we'll talk about, the specific heat of liquid water is basically 4.184 joules per gram per degree Celsius, which means you got to put in there 4.184 joules for every gram of water you have. If you think about a bathtub, it's a lot of water, right? And so it takes a lot of energy to move the temperature of that much water and see a big change in the temperature, as opposed to if you have a coffee cup, which is obviously not a lot of volume, right? So with the amount of energy is in there, we're going to see a greater sort of temperature change that's going to occur in that. So let's talk a little bit about heat. Heat can be defined as really the flow of energy from two objects that are maybe different. Heat flows from hot to cold or cold to hot. It does. It flows from hot to cold. So your kind of hotter object, if you will give off the heat and energy to the colder object. Colder object will pick up that heat and energy, and you will see a reflected temperature change of the colder guy. Probably it will go up. The hotter object will then kind of come down. Like if you took a hot piece of metal, which we'll probably do next week in the specific heat experiment. Take a hot piece of metal, right, and you throw it into some like room temperature water. That hot piece of metal is going to go into the water, right? And for the metal is going to be exothermic, right? It's going to give off all that heat and energy to the water, which is at a lower temperature. For the water, it's going to be endothermic. It's going to pick up all that heat and energy. The result of that is the hot metal should cool, right? The water temperature should come up a little bit as it is picking up all that heat and energy. So that brings us back to what we were talking about earlier about exothermic and endothermic processes. Any process that results basically in heat and energy being released is what is referred to as an exothermic process. An example of that, obviously, if you struck a match or even the Bunsen burner that you light, you obviously can put your hand near it, not on the flame, but near the flame is good enough. You could feel the heat and energy obviously being given off to the surroundings and the air. So once again, in that example, the Bunsen burner would be exothermic. All the air and everything around it would be endothermic, is picking up all that heat and energy as it does it. Endothermic process, again, is any process that absorbs energy, requires energy for it to happen. Very simple example is the lovely ice cube example, right? If we take an ice cube out, if we didn't do anything to that ice cube, because it's colder than obviously the temperature outside, it will end up picking up all the heat and energy from the outside air, starting to result in the ice cube starting to melt. And obviously it would then be endothermic for the ice cube, exothermic for the heat, for the air. Now we're going to do some calculations in this chapter and in chemistry, and there's a couple different ways that we oftentimes will represent sort of heat and energy. And two sort of ways is Q, which is heat and energy. And as I wrote up earlier, delta H, which is the enthalpy. These are two very common sort of units of energy that we end up with. And based on the actual value that you get, it's not really important in terms of determining endothermic or exothermic, but it's actually the sign of the value that you get that's important. Typically speaking, if you calculate Q or delta H and you yield yourself a negative number, that indicates that that process is most likely going to be a exothermic process. So it's going to result in a release of energy that's going to happen. If you go through calculation and you calculate Q or delta H and you yield yourself a positive number, that basically means that it's going to be an endothermic process. So it is really important. Sometimes people think it's not so important in a class like this, that, you know, when you calculate something like energy, you shouldn't worry about the sign, but you should always worry about the sign. The value, again, like I said, not super important for this determination, but it actually is the sign that's really important. So if you ever get yourself a negative number for energy, that should imply exothermic process happening. Positive value implies a endothermic process, and you shouldn't just get rid of the sign in that. Yes, sir. Delta H is known as the enthalpy. Yeah. It's actually the delta means change, so that's sometimes referred to as the change in enthalpy. But it's basically, again, a fancy way of saying basically how much heat or energy is either being released or gained. In most cases, for a reaction is how we usually will see it. Other questions? And we'll look at it a little bit later on, and we'll see it a little bit on 1A for sure. So let's take a look at another way that we could kind of look at energy. And what we see here are two energy diagrams. So these are energy diagrams. And typically on the left-hand side, we graph energy. And on the right, on the bottom, on the X, is the progression of the reaction. One is an exothermic reaction, one is an endothermic reaction. And the main way that you could tell the difference between the two is the location of our reactants versus our products. So once again, in a chemical reaction, we start with our reactants, we go to our products, which are the things that are formed. And whenever you see a energy diagram where the reactants are actually higher energy than the products, you can think of it this way: the only way for those reactants to get down to the products in terms of energy is energy needs to be given off. So energy would be released, which is why it is a exothermic energy diagram in this case. We see the exact opposite when we look at the endothermic process. The endothermic diagram on the right, we see that the reactants are actually lower in energy than the products. So the reactants are actually lower in energy than products, which means in order for our reactants to get to the products, we actually have to put energy in. So energy is absorbed. To get you there. So that is 100% of the time, if you see an energy diagram drawn like this, where you have reactants higher in energy than products, it will always be exothermic. Overall, that reaction is going to release a certain amount of energy to allow the reactants to get down to the products in terms of energy. On the right-hand side, reactants lower in energy than products, always going to be endothermic, which means heat and energy needs to be kind of put in there to allow those reactants to kind of get to the other side there. Any questions on that there? A couple of other important things on these diagrams that we will look at here. I think I'll just draw a fresh one here. So we'll do a little, so that's energy. We'll do, so that's my reactants, that's my products. Once again, here, this is going to be an exothermic reaction. Reactants are higher in energy than our products. There is a point where if you look at where the reactants are in terms of energy to kind of the peak here of the hill, this at the very top of the hill, this is what is referred to as the transition state. And at the very top of the transition state, there's usually something found there, which is sometimes referred to as the transition state complex, or sometimes people call it the activated complex. Now, first off, if we are pretty much at the peak of the energy there, when we talk about things in chemistry, kind of like life as well, when things are very high in energy, are they more stable or unstable, you think? They are more unstable, much like in life, right? We don't want to be high energy. We'd rather be just laying on the couch, chilling, right? And relaxing in a low state of energy. Chemistry works the same way. Things that are very high in energy are typically unstable. Really, the purpose of everything that happens in chemistry, a lot of things that happen, is to get everybody to kind of a lower, more stable state of energy when we make reactions occur and breaking bonds and making bonds. That's basically what's happening. So as you can see there, that transition state complex at the very, very top is like the peak of energy, which means oftentimes it doesn't really hang around a very long time because it's so high in energy. It will relatively quickly kind of drop to the other side and go to product formation. It's also why it's very difficult a lot of times to isolate that thing, because it's very high in energy and doesn't hang around, you know, a really long time. Now, when we do have a, so really quickly, this guy will usually kind of drop to the other side. When we have a chemical reaction and a chemical reaction takes place, really the only thing that is happening through that process is we're taking all of our reactants basically, and we're breaking all the bonds. And then basically they're going to reassemble on the other side in product form and make new bonds. So that's really what happens in a chemical reaction. Break bonds, make new bonds. Voila, we got new things on the other side. So as this reaction progresses, what's happening here as the reactants sort of start to climb this hill of energy, what we start to see is really our reactants are starting to kind of break some bonds, and they're also starting to at the same time make some bonds. So when we get up to that really peak there where we have that transition state complex, a lot of times that guy is something that has partially broken bonds, but also has some partially made bonds. So really intermediate kind of between reactants and products, which is why it's really unstable and very high in energy in that particular case. So like I said, very quickly, it will usually kind of come down to the other side to get back to a sort of better state of energy. There is a energy hill that the reactants really do need to climb to get to the other side. And it is that hill that I drew there in orange. It is really this hill right here. This is what is known as the activation energy. And the activation energy is sometimes abbreviated E of A. That is the activation energy. That is basically the minimum amount of energy needed for a reaction to occur. So basically, there's a couple of things that has to happen for a reaction to occur. First off, is what is sometimes referred to as collision theory. Things need to hit each other. So there has to be some type of collision that occurs. Now, it's really important to actually understand the idea that just because two things actually hit each other, it doesn't necessarily mean that you will make products. So they actually got to collide, but they actually have to collide in sort of the right orientation, kind of the active spot in both of the reactants there. So they got to hit each other in the right location, and they got to hit each other with this minimum amount of energy to allow products to be made. So there's many times where you could have collisions of reactants that actually don't do anything. It will not form any products because they either lack the right amount of energy, they hit each other in the wrong sort of location. So you really need those two things to sort of occur for a reaction to take place. So that is the activation energy there for our exothermic reaction. If we look at our endothermic one from our previous one, it would be right here. This right here is our activation energy. Between the exothermic reaction and the endothermic reaction, which one has the larger activation energy? It is the endothermic, the one on the right. The one on the left, again, is just that little bit right there. Also makes sense if you think about it being a endothermic reaction. You got to kind of put some energy in there to help some people get enough energy to get up and over to the other side. So you kind of have to help them up and over that hill, provide a little bit of energy to do so. The activation energy is also really important in terms of the rate of a reaction. It has a big effect on, a lot of cases, how fast or slow a reaction occurs. If I had a really big hill for the activation energy, would I expect that reaction to occur faster or slower than a reaction that has a smaller activation energy? It should occur a lot slower, right? For two reasons. It's a much bigger hill to climb. So just like you had to walk a small little hill, right? And then you have the giant mountain that you want to get up and over the other side. Not going to probably make it to the other side as quickly, obviously, than a very small hill. There is only really a proportion of molecules under normal conditions that have enough energy to get up and over to the other side that really meet that criteria. So having a much larger activation energy means that usually the reaction would occur a little bit slower. You oftentimes could speed up a reaction by heating it up. When I heat it up, what am I doing? When you heat something up, you're adding energy, right? So if you heat up a reaction and you're adding extra energy, what that means is there's going to be a greater number of reactant molecules that will now have enough energy to overcome that hill and get to the other side. And the result of that is you would see a much faster reaction occurring. Vice versa, if you took all your test tubes, for example, and put them all on ice before you mixed them together to do the reaction, when you put it on ice, that's basically like removing energy. So what you did in that case is you probably lowered the amount of reactant molecules that have enough energy to get up and over to the other side. The result of that, you would actually see the reaction slow down in most cases. That's typically what happens. Any questions on that? When we look at an energy diagram here, for example, the difference in energy between our reactants and our products, that is basically what is the delta H of a reaction, the change in enthalpy for the reaction. The difference between the energy of our reactants and the energy of our products is what gives us really how much net energy is either given off or absorbed in a reaction. One way you could calculate this, as I mentioned, is you could take the delta H of a reaction would be the delta H of your products, which is your final state, minus the delta H of your reactants, which is your initial state. Get that out of my way. Oops. And let's just say, for example, here, just make up some nice easy numbers. Let's just say we went across here. Let's just say that was 6. And let's say we went across here. That was 2, right? When I go to calculate my delta H for this reaction with my made up numbers, products would be 2 minus reactants, which would be 6, gives me a -4. We could call it kilojoules if you like. But more importantly, what do I see in terms of the sign? It's a negative, and this will always happen in this situation because the products are always lower in energy than the reactants, which means when you take the difference of where you ended to where you started, you'll always end up with that negative number, as I talked about earlier, and that tells you that this is going to be a exothermic process. Question on that? Now, if we looked at, say, an endothermic diagram, products and reactants. Once again, the difference between here and here would be our delta H of our reaction. And we could do the same thing. We'll just make up the same sort of numbers here for our energy. We'll just call this guy now 6 and this guy now 2. So when I do my delta H of the reaction for that guy, we're going to take our products, which is 6, minus our reactants, which is 2, gives us a +4. +4 tells us it's going to be endothermic. So when you do these type of calculations, once again, the sign is really important. It lets you know overall, are we gaining energy or losing energy? And always in that situation of an endothermic process, your products will always be higher in energy than your reactants, which means you always have a larger value for your products in terms of energy than your reactants, and will always yield you a positive value for delta H. Any questions on any of that stuff there? So you need to know the energy diagrams, what they look like, which one looks like an exothermic, endothermic, what activation energy is, and all that kind of stuff. Any questions on that? So here's an example of energy diagrams like our reactants. That's our products. So once again, our reactants are higher energy than our products. Energy has to be given off, which tells us it's going to be exothermic. And it's opposite over here, decomposition of mercury 2 oxide. That's our reactants. That's our products. So once again, in order for those reactants to get up to the products, energy has to be put in that situation. And once again, that would tell you that it is a endothermic type process. Now, sometimes chemical equations and reactions are given to you in a couple of different ways. They will sometimes display sort of the energy component of it. One way is they will actually sometimes just write in the equation, put an energy value, and that's what we see there. We see 213 kilocalories, which is an energy value. And in this particular case, the energy value is on the product side. And whenever the energy value is written into the equation, or in a later chapter, for us, it'll be the very last chapter, but we oftentimes will consider the energy as being given off because it's basically on the product side. So it is basically an exothermic type reaction when that occurs. And then any type of exothermic reaction, you could think of, and it's not correct in all aspects, but you could think of energy as like being a product, like it's being given off. It would be on the sort of the product side. And the opposite is true for an endothermic reaction. In an endothermic reaction, the value is actually put on the reactant side. And in an endothermic process, like the energy is being absorbed, we consider it to be kind of like a reactant. So if you ever see energy written into the equation, on the product side is going to represent exothermic. If you see it on the reactant side, it's going to be an endothermic. But I'll be honest with you, in pretty much all cases, in most of your chemistry classes, they very rarely will actually put the actual number in the equation. They more often than not will do something like this, where they will write, say, the combustion reaction, which is what happens when you light your Bunsen burner. And at the very end of it, which I ran out of room, they will usually just lay up a delta H value, and they will give you a number that says, hey, the delta H for this reaction is negative 335 kilojoules of energy. And by just seeing the delta H value given to you, and more importantly, just seeing that the value is negative, it should tell you that it's an exothermic reaction. Or if you had an endothermic reaction, they would write the equation at the end, right? The delta H is like positive, 125 kilojoules or something like that. And again, seeing the positive value would tell you it's endothermic. So that's more times than not how energy is usually represented with equations. You have the equation at the very end, they just give you like the delta H value, the enthalpy value. And again, it's either going to be positive or negative in that case. Any questions on that out there? All right, well, I feel like that's good for now. Sounds good. We'll lay it up there.